Okay, I guess we're a little more on time now. So next up we have Fei-Shi Wang. He's a second year master student in Peking University. His research focuses on robotics, computer vision, and reinforcement learning. His goal is to contribute towards the development of general purpose agents that understand and interact with the real world. You can take it away. You have 15 minutes, including questions.
Okay.
Yeah.
We're glad to be here to introduce our recent work, RoboVerse, towards a unified platform dataset and benchmark for scalable and generalizable robot learning. And I'm the co-first author of this paper. And this work is led by UC Berkeley, Peking University, USC, and Beijing Institute for General Artificial Intelligence, and many other institutes. And this work is accepted by RSS 2025. And yeah, so the motivation of this work is that nowadays we are talking about robot learning. So that turns out dataset and benchmark is very important. And we have seen that large-scale datasets combined with well-established benchmarks has fueled the rapid advancements in NLP and computer vision. So how do we replicate such success in the field of robotics? And yeah, so generally there are two kinds of data sources, real world and simulation. And collecting data in real world is time consuming and resource intensive. It is also hardware dependent or modality specific. And benchmarking in real world is even harder because it faces the challenge of reproducibility. And I believe the reproducibility is the key for the benchmark. Right? So, and to address these problems, I think simulators present a promising alternative. And we have seen a lot of recent works that have shown the great potential and ability of simulation environments and build upon different simulation platform and develop their own data set and benchmarks. However, they are still segmented into a fragmented ecosystem. And by fragmented, I mean they are based on different simulator backends, Mojoko, ISAC, or Sapien, something like that. And their data format is not shared, and the efforts that put into the existing platforms cannot be shared and communicate with each other. So I believe this somehow hinders the progress of the robotic simulation. So we ask, is it possible to merge all these efforts and combine the strengths of different works together that create a unified platform? And on top of that, we can create a really high quality, large scale data set and unified benchmarks. So to this end, we propose RoboVerse. As you can see from this picture, we have combined a lot of different tasks and data from existing classic works. And also the RoboVerse support different simulator backends and integrate diverse tasks and demonstrations, and also support different robotic embodiments. So how do we do that? I will give a quick overview and dive into details later. So RoboVerse consists of three parts. First is the simulation platform called Medicine. And on top of that, we build a high quality data set and unified benchmark. And we designed Medicine into three layers. And the key concept here is that we make everything to be the simulator agnostic. So to launch an application program, we start from a universal configuration system. This configuration system is simulator agnostic. It generally tells what is in this environment, and what object is in this environment, and who is performing the tasks, which is the agent, and what is the goal of your task. Maybe there are some success conditions and real world functions. And how do you perceive this environment? There are kind of camera sensors or tactile sensors. And finally, what is the overall physics law in this simulation? And these components are all simulator agnostic, and we can describe it in a universal way. And we then translate these configurations into different simulator backends. And as you can see here, there are many existing simulation backends are supported here. And finally, we provide a user-friendly gymnasium environment for the robot learning interface. And our design enables three key capabilities. The first one is cross-simulator integration. It means that with one single piece of code, you don't have to change the code. You can directly switch the simulator from the command line. And the second capability is hybrid simulation. It means you can integrate the strengths of different simulators to form a stronger one. For example, you can integrate the physics engine of Mojoko with the renderer of Isaac Lab. And as we know, they are the best in their each field. Like Mojoko has the best physics engine, and Isaac has the best renderer. And now, because we use the aligned backends, we can combine it together to form a new kind of hybrid simulator. So again, you don't have to change the code. You can achieve it with the same piece of code and switch the hybrid simulation in the command line. And finally, our framework also supports diverse robot embodiments so that the data collected in one robot can be reused in other. And yeah, here's like the quick overview about how we connect the simulator backends and the gymnasium environment. And this is not the real code, it's just the pseudocode, and just to show how the API is designed. And the key here is that we abstract the states from the simulators and use it to communicate between each others. So the key functions here is the set states and get states function. And as above, we show that some property of our configuration systems. So built upon this unified infrastructure, we migrate diverse sources of tasks and use some data augmentation techniques, and finally build a high quality data set as well as a unified benchmark. So I will then introduce the dataset part and the benchmark part. So for the dataset part, there are mainly three sources of data, three kinds of data. So the task and asset and trajectories. And the main source of all these three kinds of data is migration. So we simply download all the data from the existing benchmarks, and we combine it into our unified format. And here are the list of the supported benchmarks, and some of them are partially supported. And there are also many other ways that we can collect the data. For example, teleoperation, and we support our own designed phone app to perform the teleoperation. And something wrong with the slides. Okay. Yeah, and you can use it to complete.
Thank you. I mean, it's including questions.
Okay, thank you. Yeah, you can complete these tasks. And also we support mocap system, VR, keyboard, and joysticks. And thanks to the unified configuration system, we can describe a task in a unified way. And all the task is described using the code format we designed, so that we have enough to prompt, we have enough examples to prompt the LLM to make it generate new tasks. And yeah, and this is the example of the LLM generated tasks. You can see it really understand the spatial relationship of these assets. And for example, if you if you have a bottle on a table in a Kelvin dataset, and the LLM agent somehow can understand, okay, that level of height is the table height. And if I want to combine the table with a new object, it will also be on that level of height and in the range of the table. And we also support the real-to-sim pipeline to reconstruct the real-world scenario and reconstruct it with 3DGS and verify our reconstructions and trajectory in the simulator, and finally render it with 3DGS. You can even tell that this is from 3DGS. It looks like no different from the real world. And here's another example. And finally, we use our hybrid simulation capabilities as well as a lot of data augmentation methods to augment the trajectory and augment the background scene, and also create the data set with the Mojoko physics engine and the Isaac Lab renderer. So we get the highest quality tasks and trajectories that use the Mojoko physics engine and the Isaac renderer. And here's a comparison between the RoboVerse dataset quality and previous dataset. You can see the diversity and render quality is well improved. And in total, we provide more than 500K trajectories, more than 200 tasks, and more than 5K assets. And for the benchmark part, okay. For the benchmark part, here's an example of reinforcement learning results. I'll go through it very quickly. And we also do some interesting applications, like training the world model with RoboVerse synthetic data combined with Droid. We find it got improved from the results that is trained solely on Droid dataset. And we also train a VLA grasping policy and from our RoboVerse data, using our RoboVerse dataset, and we see the directly sim to real to the real world. And we also support the seamless sim-to-sim verification, and the policy is finally deployed to the real world. So the takeaway is that we believe that the fragmented ecosystem could hinder the progress of robotics, and to address these problems, RoboVerse aims to be a complete toolchain that developers and researchers can use to collect data and many other downstream applications. And we also hope that RoboVerse could be a standard development benchmark or protocol for the field of robot simulation. And your questions are welcome. And for more details, you can visit our project page and GitHub. Thank you very much.
Maybe stay one more second. Does anyone have questions? Okay, if not, yes. And exactly.
Okay, thank you for your presentation. I have a question about the future of your benchmark of your simulators, meta simulation tool. What about highly dynamic sense when the scene changes very dynamically, when we have a lot of agents, a lot of movable objects? What is plans of development of your benchmark? Could you tell?
That is a very hard problem. I believe that existing simulation environments doesn't have the have the benchmark for that kind of tasks. And I think what rovers can really do is that it can combine the existing data together so that we can combine it in a more organized way to find the best suit asset for the specific task. And we can also through our simulator capability, it is possible that we can compare the physics engine's dynamics, maybe across eyesight or Mojoko, and we can find the one that is the most accurate. I mean, Mojoko is already accurate, but it is possible to compare it fairly, so that I think with that capability, the evaluation could be more fair. Yeah, thank you. Thank you.
Okay.